Good morning to all of you. Today we are going to talk or discuss on the topic of the problem analysis. Means previously in yesterday's class we have talked on the problem state, problem search, this type of particular things, right? Now, depending upon that, we are going to take a problem. We are going to analyze that particular problem and see how the things goes on. So suppose as an example, let us first have an example. So all of us heard or somewhere in previously have heard about a game that is called a missionary and cannibals game, right? So we are going to talk on that missionary and cannibal games, right? So what is the scenario in the missionary and cannibal games? Let me first explain that what is the idea of the missionary and cannibal games. That it illustrates three missionaries and three cannibals. First, let me write the problem. Three missionaries and three cannibals. Three missionaries and three cannibals are wished to cross a river. Are wish to cross a river using two-person boat. So on a boat, at a time, there can be two-person cross the river, and we have three missionaries and three cannibals. Now, that if at any time the cannibals outnumber the missionaries, if at any time the cannibals outnumber the missionaries, then what happened? On the either side of the river, they will eat the missionaries. On the either side of the river, they will eat the missionaries. So this is the scenario. Now, there will be a sequence of boat trips that to be performed by which everyone go to the either side of the river without any missionaries being eaten. Now we need to perform a option, perform a solution. We need to find the solution here by which no missionaries get eaten and all of them can actually cross the river on the either side. Now if I draw a particular scenario on that, so the scenario something looks like this. So suppose there are three cannibals, okay, and three missionaries. They need to cross the river on the other side by using a single boat. Now, at each and every time, the number of cannibals, the number of missionaries needs to be same. If at any moment, suppose these are my cannibals, these are my missionaries. C for cannibals, M for missionaries. So if at any time the number of cannibals are greater than the number of missionaries, then the missionaries will be eaten by the cannibals. So the task or the problem will be failed. So now what is the step representation? First, we are going to check one by one what is the scenario. First, we are going to find the state representation. So what is the state representation here? The state representation is boat position. First one is the boat position. So in the part of this boat position, some original or the final side of the river, means Original means where the cannibals and missionaries are present. So original and the final side of the river. Original and the final side of the river. This is the number one state representation. Now, number two, what is the next state representation? Number of missionaries and the cannibals on the original side of the rivers. Number of missionaries and number of cannibals on the either side of the river. Three. The last state, that is start. We need to start with the side from 3 to the goal of nil 0 0. So from the starting side, so we are starting with the concept of 3 cannibals, 3 missionaries, and my target is, my goal is to reach 0, means all the cannibals and all the missionaries need to be crossed the side and needs to reach on the other side. But the constraint is that the number of cannibals should not be number of missionaries. It can be equal to or less than 2, but the number of cannibals cannot be greater than from the missionaries. Now, how we can do that? How we can do that, right? So let us take the operators. Let us check the scenario, right? First of all, the operators. So the operators. What is the operators that is present here? That is, suppose first time 2 missionaries cross the river. The first scenario here that we write that 2 missionaries cross the river. First of all, 2 missionaries if cross the river, then we cannot actually go for it. Why? Because if 2 missionaries cross the river, then in the one side there is number of 3 missionaries and one cannibal. 3 cannibal, 1 missionary. So the missionary will be eaten. Second, it can happen. So I am writing the first scenario. What can be done? What can be done? So first time I am taking 2 missionaries, that cannot be possible. So this scenario is not possible, right? It is not possible. Now my second scenario. Second scenario is 1 missionary and 1 cannibal. 1 missionary and 1 cannibal. So this scenario can happen because on the either side there is 2 missionary, 2 cannibal, they cannot eat, and 1 missionary, 1 cannibal is there, right? So no issue on that. It can happen. I'm not telling that it is the way, it can happen. But when it will be reached on the other side, one of them needs to be drop out because one of it have to take it back to the other side. So at the same time, one person need to be in the boat to cross the river. So 1 missionary and 1 cannibal will be there. Next, the third scenario, there can be 2 cannibal. Next, the third scenario will be 2 cannibal. Fourth scenario, we can choose 1 missionary and 1 cannibal. But 1 missionary, 1 cannibal cannot get because they need to take the boat on the other side, right? So what we can do, this is a statement and we need to find out a solution by which we can actually do it, how we can perform it. So next, the thing is the control strategy, how we can control this strategy. Here, the word, the search refers to the search for the solution of the problem space. Now again, we need to search for the solution of the problem space. We are going to search for the problem of the solution space. The word search here is actually representing the search for the solution in a problem space. And this search actually proceeds with different type of search control strategies. The search proceeds with different type of search control strategies. So this strategy is defined by picking the order in which the nodes expand. So the strategy can be defined. The strategy is defined by picking the order is defined by picking the order in which the nodes expand, So strategy is defined by picking the order in which the nodes expand actually, right? So these search strategies are evaluated. These search strategies are evaluated along with some following dimensions. What are the dimensions? Completeness, time complexity, time complexity, then we can say space complexity. These are the terms that is actually needed in this particular part, right? Space complexity, on which the strategies actually depend, here. Now, this search related terms, the algorithm performance and the proximity, some factors, several type of factors are present here, right? So the thing is that we have different type of several data structures and algorithm properties that we can use here. The tree structure like graph, stack and queues, push pop notification, several type of these type of things can be represented. Now, if we talk one by one, what is the advantages of tree structure? What is a tree structure? If we talk about the tree, if we talk about the tree is the way, a simple way for organizing the objects related in a hierarchical fashion. So tree is a way of organizing the objects related in a hierarchical fashion. So it is a type of data structure in which each element is attached to one or more elements. So tree is a type of data structure Tree is a type of data structure which is actually in which the each element is attached to one or more element in which each element is attached with one or more element. So tree is a type of data structure in which it is attached with one or more element with beneath it, right? So tree is helping us for this connection between elements are called the branches. The connection between each elements are known as the branches, and it is often called the inverted trees. This tree is often called as inverted trees because it is drawn with the root at the top. So tree is often called as the inverted trees because it is drawn with the roof at the top. So these elements that have the binary tree, there is several type of properties of this particular trees. What are the properties? This tree we can say is a special case of graph. We can say this tree is a special case of graph. Tree is a special case of graph. And this topmost node in a tree called the root node. The topmost node is called as root node. The topmost node is called here as the root node, and all the root nodes or operations on the tree begin. So this each node has either one or more than one child nodes and which are below of it, and this nodes of the bottommost level is known as the leaf nodes. So then we have some particular provision of stack and queues. We have another particular point that known as stack and queues. So the stack and queues, we can say that it is a data structure that maintain the order of last in first out or first in last in first out and first in or first out respectively. So depending upon the scenario, either it can be stack or it can be queue, it has a several type of option. But the stacks and queues are often implemented in linked list in some possible implementation ways, right? So the thing is, if we talk about stack, we can say if I rather talk about this particular point stack, we can say last in first out. The stack, it is known as last in first out. So it is an ordered list, a sequence of items piled one on top of the other. So what happened? This is a sequence, this is an order list, a sequence of items. What happened? The items are piled one on top of the other. The insertion or deletion are made from the one end only. The insertion and deletion are made from the one end only, that is called top. So whatever, that's why the term that is last in, first out. The data that will be the item that will be entered last into the stack will be coming out first. That is why it is known as last in first out scenario. So we can say that it is a type of basket where if I put some clothes into the basket in a manner in an ordered way, then the last cloth that will be put up into the basket will have to take up first in order to get the last one, or in order to get the beneath the last in the beneath of the basket, right? So this is why that is known as the last in first out. Now this insertion and deletion are made at one end only, that is called top. And if this stack that is S equal to, we can say different items A1, A2, AN. A1 is the bottommost element, and all operation takes place from the top portion. So there are two particular things happen. Two operation that is happening. One is pop, another one is push operation. There are two operations that is happening, pop and push. There are two operations that is happening, pop and push operation. So this pop and push operation is taking or helping us to put some item into the stack or to add to delete some item from the stack. So this pop operation removes the item from the top of the stack. The pop operation removes the item from the top of the stack, whereas this push operation adds an item on the top of the stack. Right? So this is the simple scenario for push, pop, and in the particular part of stack. Now the second part, that is queue. Now the second part that is known as queue. It follows the scenario of first in, first out. The queue is following the scenario of first in, first out. Means we can say that it is an example of a cinema ticket counter where the person who is giving the line first will come out from the scenario and the first one, right? So first in, first out. The concept here is that is first in, first out. So it is also an ordered list or sequence of items that have restrictions about how items can be added or to remove from the list. But in the scenario, in the case of the stack, there is only one end where all the operation will be happening. But in the case of this queue, it has both ends. So in the particular queue, a queue has two ends, but the scenario is one from the one end, one will get inserted, and from the other end, one will come out. So the insertion takes place at one end, that is called rear or the back side. And in the front side, the scenario, that is the deletion will be happening. So insertion and deletion, the insertion takes place at one end called rear or back, and deletion that will be takes place on the other end, that is called front. And if this queue has different type of items, all operation takes place at one end of the queue or the other. So there is two things that is known as DQ and NQ. In the part of this queue, there is two things present. One is known as DQ. Second one is known as NQ. So what is this DQ and NQ is? DQ is an operation to remove an item at front of the queue. DQ is an operation removes an item at front of the queue, and the NQ is an operation that adds an item to the rear of the queue. This NQ, DQ is operation remove the item, and NQ is operation adding an item to the rear of the queue. Now the part, there is this next part that is known here as search. It is a systematic examination of states to find the path for the start or route of the goal scenario. Right. So this state change, state representation, state space, we have talked a lot on this particular things in from yesterday's class also. Now this state space, we are talking about problem description and the state space. The problem, whatever the problem is, or whatever the state space on the particular point of the problem, a state space should describe everything that is needed to solve a problem and nothing that is not needed to solve the problem. Means a state space. So a state space should describe everything that is needed to solve the problem. Also, those things that may not be needed. Means in a simple term, we can say that each and every, whether it can be a very important part or whether it can be not, all the things need to be present in our state space, because we don't know while we are going to perform, we are going to find a solution of the particular problem, whether this is a very important thing or this is important data to solve the problem or not. So whatever the data, whatever the details are present, all the things need to be present in our state space. And this description by a desired test may be complete or a partial. Now there is some operators that is consist of preconditions and instructions. There is some operator operators that consist of some precondition and instructions. So this precondition, what is this precondition? It provides some partial descriptions of the state of the world that must be true in order to perform the action. So precondition provides a partial description of the state of the world that must be true in order to perform the action. So whatever action we are going to perform, that should be in the part of this precondition, and instructions tell the user that how to create the next state, and instructions tell the user that how to create the next state. So two things: precondition, that is providing some partial differences descriptions of the state of the world that must be true in order to perform the actions, and instructions tell the user how to create the next state. Now this operator should be as general as possible to reduce the number. So here the thing is, elements of the domain has the knowledge of the starting point. So here the term that is present, that is elements of the domain. Elements of the domain, and another term that is actually present here, problem solving. Elements of the domain and the problem solving, these are present here. Elements of the domain is the knowledge of the starting point. Problem solving is finding a solution to find an ordered sequence of operators that transform the current state into a goal state. Then there are restriction and solution, that is quality of any optimal or finding the shortest sequence, least expensive sequence, or any sequence that is quickly as possible. So restriction or the solutions of that particular, by where we can easily find out, we can minimal optimization on it. So this can also be explained with the help of some algebraic functions also. Now, this problem characteristics, we need to find out the characteristics of this particular problem. To use any kind of search for the problem solving, we need to analyze the problem with some following considerations. What are the considerations? First one, decomposability of the problem into a set of independent smaller sub-problems. First one, segregation of the problem into the smaller sub-problem. So segregation of the problem into the smaller sub-problem, right? Second one, possibility of undoing solution step, possibility of undoing solution step. Third, predictability of the problem universe, predictability Fourth, possibility of obtaining an obvious solution to a problem without comparison of other solutions. Possibility of obtaining an obvious solution. Possibility of obtaining a obvious solution. Fifth one, these are the scenario, these are the consideration that we need to analyze for any type of problem solving. Role of knowledge, nature of solution process. Then there is role of knowledge and nature of process. So these are the these are the analyzation parts that we need to analyze, that we need to find out for the problem solving. So this problem can be decomposed or can be segregated into sub smaller part, can be segregated into sub smaller part as we need here in for the better solution. So find a particular solution, we need to explore all the possible characteristics, all the possible aspects to get a particular solution, to find out the best solution of this particular problem. Now the thing is, when you actually trying to design a solution for the program or design a search for the program, there are some issue may arise. So what are those issues we need to look? That if we're using any type of graph or tree scenarios, a tree can be searched forward from the initial node to the goal state or backwards from the goal state to the initial state. But to select some applicable rules, it is very critical to have an efficient procedure for matching rules against that particular states. Also, we need to check some duplicates nodes, observe that whether all the nodes are already generated or any new nodes are present. If any duplicates nodes are present, we need to cut it out. Or if it exists, we need to add it already graph. If already exists, then we need to ping it out. Set the node is being expanded to the point where it is already extended. So these are the several type of solutions that we need to find out, right? So these searching techniques, these heuristic search techniques we call, these are two part. One is uninformed search algorithm or brute force algorithm we can say, and second one is informed search algorithm. So heuristic have two type of things, uninformed search algorithm, also informed search algorithm. So this two type of scenario is present, uninformed search algorithm and informed search algorithm, right? So what happened in uninformed search algorithm, that it search through the search space of all possible actually exploring the possible items or the candidates for the solution, checking whether each candidate satisfies the problem statement. So uninformed search algorithm or brute force algorithm actually search through the search space all possible candidates for the solution, checking whether each candidate satisfies the problem statement. Or informed search algorithm, that it is a heuristic function that is specific to the problem, apply them to guide the search through the space to the search space to try to reduce the amount of time spent in searching. So this heuristic will make an informed search dramatically outperform any uninformed search. For example, any TSP, traveling salesman problem, or giving some prominent intelligence search algorithm like BFS, DFS, greedy search, generate and test search. This type of several searching techniques or algorithms can be used to find out a particular option, find out a particular solution. So we have heard or we have already learned about the topics like BFS in our data algorithm, data structure and algorithm, BFS, DFS, the depth first search. So then we have several type of this. So we will talk on this particular part again. So BFS, the full form we know as this breadth first search. What happened in the BFS? That is a search strategy. So this BFS, what is this BFS? Known as breadth first search. So in the part of this best first search, what happened? That it is a strategy at higher layer of a decision tree that is searched completely before proceeding to the next layer. And in this strategy, no visible solution or no viable solution are omitted, and therefore it is guaranteed optimal solution will be found here. And the strategy is often not feasible when the search space is large. So simple algorithm, we need to create a variable that called list, set it to the starting state, loop it until a goal state is found or list is empty. Remove the first item from the list, and if the list is empty then we need to quit, or for each and every patch rule we cannot do so. This is a simple algorithm on this particular BFS. And what is the advantages if we talk about of this BFS? That it guaranteed to find an optimal solution, can always find a goal node if one exists. This is the best advantage of this BFS, that it guarantees to find an optimal solution. And disadvantage is high storage requirement, exponential with the tree depth. So requirement or storage or space requirement is very much high in the part of this BFS. So say we can say that BFS is a good strategy with which highest layer of the decision tree is searched, and also it is completely before proceeding to the next layer. But in the strategy, no viable solution are omitted, and for therefore the guaranteed of optimal solution is found. The strategy is often not feasible when the search space is large. So there is a backend or there is a drawback. So when the large space is large, then at that particular time we cannot find any solution. We cannot find a feasible solution. So at that time, no good solution we can find out. So up to this particular part, up to this BFS, we are going to talk today. We are going to stop our discussion today here. We will continue from the DFS in the next part, right? So I would like you all to write your names in the chat box for your attendance purpose. So write your names in the chat box. So today we have talked on the problem analyzing, how we can put the scenario into a problem state space, how we can go with the scenario, what is the scenario, how the problem statement, what is the searching algorithm techniques. We can also look, one thing is similar, that whatever the searching algorithm techniques we are talking about, it was already in our data structure and algorithm. So one thing we can say, that data structure and algorithm is a very important part, very important topic that is very much present in every place, right? So data structure and algorithm, we need to keep a very good knowledge for on that particular subject. So now this is all for today's class. Thank you all for joining into the session. And one more thing, stay safe and take care as the cases of the COVID is rising day by day. So all of you stay in your home and stay safe. Take care.